Very happy to be here. Thanks for the invitation. My name is Harm van Seijen. I'm a research scientist at Maluba. Maluba is a company specializing in natural language processing. And I'm going to talk today about using deep reinforcement learning for dialogue systems. Let's see if the clicker works. Perfect. Okay, so let's start with the problem. So if you have a user that interacts with a spoken dialogue system, then the user input goes to a very specific pipeline. So if you have, for example, a restaurant reservation system, the user might say something like, "Hi, do you know a good Indian restaurant?" Then that goes into a natural language understanding unit, which translates it into a machine readable format. For example, inform food is Indian. This then goes into a state tracker, which keeps track of everything that has been said since the start of the dialogue. And this goes into a policy manager, which creates a response to the dialogue state. For example, request the price range. This then goes into a natural language generation unit, which generates the response in natural language. For example, sure, what price range are you thinking of? Now, if you look at this pipeline, then the heart of the system is really the policy manager, which comes up with a proper response. And in traditional systems, they used a rule-based system for that. But when systems got more complex, and especially when they started to take into account probabilities, because all these modules, they create certain errors. They are not 100% sure. So if you want to take into account the probabilities of everything that a user could have said, then you get this very complex state, and it becomes very challenging to come up with a proper response. So we want to train this from data, ideally. So this is the central question of this talk, is how to train the policy manager. And as you can already guess from the title of this talk, we're going to use reinforcement learning for that. So just a short overview of this talk. I'm going to first talk about what is reinforcement learning, so on a very high level. Then I'm going to get a little bit more technical and look at some of the solution strategies for reinforcement learning. And then I'm going to talk about some specifics for if you want to apply a reinforcement learning to dialogue systems. So first, what is reinforcement learning? In one sentence, I would say reinforcement learning is a data-driven approach towards learning behavior. So it's not so much a method, but it's a problem class, and it's a subclass of machine learning, just like supervised learning and unsupervised learning. So all of these classes you can use deep learning for, and when you combine reinforcement learning with deep learning, you get deep reinforcement learning. So I'm going to talk about that a little bit later. So first, to talk a little bit more what reinforcement learning is, I want to make a comparison with supervised learning, because I'm going to assume most of you are familiar with supervised learning. So our goal is to learn behavior, and behavior is nothing more than a mapping from environment states to actions. So you might think, why can't we just use supervised learning for that? Right? It's just about estimating a function. Now, in principle, you could do that, but supervised learning is especially great if the following two conditions hold. It's hard to specify the function, but it's easy to identify the correct output. So, for example, again, a cat example. Suppose you have the task of recognizing cats in images. It's very easy for us to look at images and to label whether there's a cat in the image or not, but it's very hard to define a function that maps the pixel values to the correct label. So this is something that supervised learning excels in. Now, the problem with behavior is that in many cases you don't know what the correct output should be. You don't know what the correct action is in response to a particular state. So like I mentioned before, if you have a dialogue state, which is really a probability distribution over all the possible things a user could have said right now and in the past, then that's a really complex state, and you don't know really what the right response is in that case. So that's why we turn to reinforcement learning, because reinforcement learning you can use when it's not only hard to specify the function, but it's also hard to identify the correct output. So all you need to do is to specify a behavior goal. So just to show a classical example from reinforcement learning, the double inverted pendulum. So here the task is to balance a pendulum upright and by applying torque to the joints. So the state in this case is the angles of the two rods and the angular velocities. And yeah, you have to apply the correct torque such sorry about that. I'll be careful. So you have to apply the correct torque such that the pendulum balances upright. So this is an example where if you would ask a person, okay, given this particular state, what's the torque you have to apply? It's a very hard question. But it's very easy to specify your goal. You would just want the pendulum to be upright. So this is something that reinforcement learning excels in. And yeah, like I mentioned, it's the same for the policy manager. That's another example. It's very hard to specify the correct actions, but it's easier to specify your goal. Maybe you just want to complete a specific task, or maybe you want to do something else. But yeah, so that this is where reinforcement learning excels in. If it's easy to specify the behavior goal, but it's hard to identify the correct output. So that is one of the advantages, is that it does not require knowledge of a good policy. Another advantage is that it does not require labeled data. So all you need to do is specify your goal, and then the system, by interacting with the environment through a trial and error process, learns automatically how to find good behavior. So another advantage is online learning, and that means that it adapts to changes in the environment. If you take the pendulum example, for example, it could happen that if you balance this for a long time, then the actuators, they don't work so well anymore, so you have to change your policy. And with reinforcement learning, you adapt automatically to this changing environment. Whereas with supervised learning, you would have to retrain your system, basically. So that's yeah, another big advantage of reinforcement learning, that you can do online learning. Now, some challenges. Of course, there are also challenges. And so one of the challenges is that it requires a lot of data. Yeah, just yeah, it can require like yeah, it just requires lots of data. I'm trying to think of an example, but yeah, you can imagine if you have a real system like a dialog manager, that can be an issue. Another challenge is that the sample distribution changes during learning, because the samples that you see, they are generated by a policy, and you're trying to optimize your policy, so the policy changes during learning, so also the sample distribution changes. And finally, samples are not IID, so they are strongly correlated, and these last two challenges, that's especially a problem if you want to combine it with deep learning, so if you want to do deep reinforcement learning. So yeah, I'm going to come back to these, discuss some approaches that you can do to deal with these. But yeah, so these are the challenges. So yeah, that was a very high-level overview of what reinforcement learning is. In the next part, I want to go a little bit more technical and look at some solution strategies. So how can you find a good policy? From scratch, basically. How can you go about that? So I'm going to start with a couple of definitions. So an RL problem is typically modeled as a Markov decision process. This can be described by a 5-tuple, which consists of S, the set of states, A, the set of actions, P is the transition probability function, telling you the transition probability from one state to another state if you take a particular action. R is the reward function, which tells you a reward corresponding to a particular transition, and gamma is the discount factor. Now, the goal of a system is typically to maximize the return, which is defined as the discounted sum of rewards. So we define a policy as a policy pi as a mapping from states to actions. And a policy has two value functions associated with it. It's a state value function, which gives you the expected return conditioned on the state. So that means that if you are in a particular state and follow that policy pi, what is the expected return? and the action value function, which gives you the expected return conditioned on the state action pair. So it means that if you are in state S, take action A, and then policy pi thereafter, it gives you the expected return for that. So finally, an optimal policy pi star is a policy whose corresponding value function is the optimal value function. So it basically means that from every possible state, it gives you the maximum expected return. So that's the one that we want to find. So now before discussing how you can find this policy, I'm going to talk about a related problem, which is estimating the value function of a particular policy pi from samples. Because once you have a good method to do that, it's a lot easier to find a good policy. So I'm going to start with this. So our problem is basically to find a weight vector theta such that phi hat, your approximation, accurately approximates phi pi for relevant states. So we can define an error function as a squared error over the stationary distribution, and then we can use standard stochastic gradient descent, giving us the following update rule. Now, you see that in this update rule, phi pi is still part of that update. And in our case, we don't know phi pi, because that's the value that we want to estimate from samples. So in reinforcement learning, you're going to replace that phi pi with an update target, ut, which gives us the following update rule. And this is one of the most general update rules used in reinforcement learning. So then the question is, what should your update target be? Well, there's actually many different possibilities. So one example is to use the full return, which would give you an unbiased estimate of your value, but it has a very high variance typically, because in general, environment is stochastic, which can cause a lot of variance. So this means that if you use this update target, typically learning is very slow. So what people often do in reinforcement learning is they use an update target that bootstrap from other value estimates. So you see an example of that below. So the lowest update target there, it just takes the reward plus gamma times the value of the next state. Now, you have no longer an unbiased estimate in this case. It's a biased one, but it has a very low variance, and it often results in much faster learning. So, and this technique of bootstrapping your update target on other value estimates is called temporal difference learning. So now we have a method to estimate a value function from samples. And you can do that for the state value function v, but also for the action value function q. And with that method, you can create a method to find an optimal policy in an iterative way by iterating between policy estimation and policy improvement, which works as follows. You start with a random policy, then determine the Q function for that policy, and then you can perform a policy improvement step, which means you can define an improved policy by taking in every state the action with the highest Q value. And this is guaranteed to give you a better policy than the one you had. So now you have a new policy pi, and you can again do policy estimation for that, determine the Q values, and again perform a policy improvement step. And by iterating between these two, you're going to converge to an optimal policy. So, so this is one way to obtain that. A more general way is you actually don't have to do full policy estimation, a full policy improvement, but you can also make a very small step in the right direction. And this is, for example, used by a classical RL algorithm called Q-learning, which combines a partial policy evaluation step with a partial policy improvement in a single update by using the update target that you see below. It uses the reward plus gamma times the maximum Q value of the next state. By using that update target, you're combining policy estimation and policy improvement in a single step. Partial policy improvement. So now on to deep reinforcement learning. So what is deep reinforcement learning? Well, it's nothing really that special. It's just reinforcement learning where you use deep learning to estimate the Q values. So it became very popular since 2015 when DeepMind came out with a Nature paper on a method called DQN. And the main result of that was that with the same network architecture, they learned to play a large number of Atari 2600 games at above human level. So, and if you look at the algorithm DQN, then, well, it's just a variation on Q-learning in a sense that uses deep neural networks to approximate the Q function. And it has 2 extra tricks to deal with some of those challenges that I mentioned before. So one of the challenges was that your samples are correlated. So what they do is they use experience replay to deal with this. And that means that you store your samples that you observe in a buffer. And for your updates, you draw at random from this buffer, such that the samples are no longer correlated. So that's one of the techniques that is used. And another trick they use is that you use 2 networks, a regular network and a target network, to mitigate non-stationarity of the update targets. So they have the target network that is just updated very slowly. And the reason is just to kind of slow down the variance, such that yeah, things change more slowly and you get better stability. So yeah, it just uses these two tricks. So this brings me to the last part, applying RL to dialog systems. So yeah, we looked at high level at some RL methods. We looked at some specific techniques. So now let's go back to our original problem. We want to train the policy manager. So there is one challenge there, which I mentioned as one of the challenges of RL, is that you need lots of data. Now, if you have a game like Atari, that's not really an issue because you can just put it on a supercomputer, run it faster than real time, and let it run overnight. But if you want to train a policy manager, it's really an experiment with the real world, and you can't really do that trick. It can take a very long time. So what people typically do is they do the training in 2 phases. So they first train a user simulator from offline data, and then they use this user simulator to train a policy manager. So yeah, by this 2-step training, you avoid that problem that you need lots of training in the real world. Of course, yeah, how to get a user simulator, a good user simulator, is also a very challenging problem. So it's not by all means an easy one, but it's more manageable this way. So why would you want to use deep reinforcement learning for a dialog system? Well, as you mentioned before, if you have the dialog state, which is a summary of the whole dialog history, it's in typically you don't observe that state exactly, but you observe a distribution over all possible states, because you don't draw errors in the different modules. So you just have a distribution over all the possible things a user could have said, and which is a really complex state. So what you're doing reinforcement learning really on a belief state, which encodes like this probability distribution. And this is a very large continuous state space. So to make the task tractable, people typically discretize it into something called a summary state space. But to make the summary state space, it requires very specialized knowledge. And yeah, you need a lot of domain knowledge for that. So now we show that if you use DeepRL, you can actually apply reinforcement learning directly on a belief state space due to its strong generalization properties. So you no longer have to use this trick of the summary state space. Moreover, with pre-training, a DeepRL method can become even more efficient. So I want to end with some results. So we compared a number of deep learning methods with and without pre-training on Policy Manager. So you see DQN, which I discussed. You have DDQN, double DQN, and Deep Advantage Actor-Critic. And on the y-axis, I've plotted the average dialog length. So this is something you, in general, want to keep short if you have something like a restaurant reservation system. and you have the average reward, which in this case was +1 for successful completion of the task, -1 if the task wasn't completed, and there was a small negative reward for every turn. So that is what you want to have high. So what you can see from these graphs is that you can, with deep learning, you can train very efficiently already with a couple of hundred training dialogues. You can learn a good policy. And with pre-training, it becomes even more efficient. So yeah, these are the high-level results. I'm going to refer to a paper if you want to know more about it. So a summary of my talk so far. Reinforcement learning is a data-driven approach towards learning behavior. One of the advantages is that it does not require knowledge of a good policy, and it can be used for online learning. Combining reinforcement learning with deep learning means that RL can be applied to much bigger problems. And constructing a good policy for a modern dialogue manager is a challenging task, but deep RL is the perfect candidate to address this challenge. And that's the end of my talk. Here are a couple of references for further reading, also some code examples if you want to play with it yourself. Thank you very much. Yeah.